Okay, welcome everybody. Today is Saturday, the 17th of December. This is Dallas Personal Robotics Group, and we are today having our monthly session. And today we have the benefit of presenters of seeing Iron Rain, our favorite team from Dallas. They're going to present their current kind of ad hoc status and request our feedback. So we'll see what we can do going around the table. And I think that's about it. There's nothing else in the regular slides to share. So without further ado, I would say Iron Rain, welcome again. Hi again and welcome again. And the floor is yours. How's it going?
It's going well. Thanks for asking. So,
wait, before they get started, I just want to note that they do have a presentation that they worked up last night. And so there's going to be a lot of slides here. And one of the things I'd like you to sort of pay attention to is the fact that they're only going to have 5 minutes to give an uninterrupted presentation during their actual judging sessions. And so I'd like you to sort of pay attention to the slides as they come up and the descriptions around them, and sort of mark in your minds which ones are the most impactful, because they're going to have to cut this down quite a bit in order to meet that 5 minute, right? So they've got to decide what to keep and what to toss. And it'd be great to have your feedback on that as well.
Duly noted.
All right, go ahead, guys.
all right. Thank you for giving us this opportunity. We are Iron Rain. I'm Gabriel.
I'm Trey. Vince. Leo.
I'm Arav.
I'm Anuya, and this is Georgia. Her voice is non-functional right now, so I'll be speaking through it.
All right, let's go ahead and get started with the new season overview. So we're going to take a quick look at the new game field here. As you can see, it's more simplistic this year. It consists of 9 ground junctions, 4 small poles, 4 medium poles, and then 4 large poles. We also have our scoring elements in the form of these cones that allow us to just score on the poles or the ground junctions. So not a lot of complexity, really, with this year's game. I think now would be the time, if you haven't seen it already, to play the animation.
Is this audio? Is there no audio on this? Let's see. Nope. It's not letting me change the audio. Okay. You know.
Isn't there a Zoom setting for share computer audio?
Yeah, we can. I'll try that.
The audio itself just isn't playing, like on our computer either.
We can't hear it either. That is so weird.
Is it a volume thing?
Nope, volume's all the way up.
Your audio was on mute. It may still be.
Okay.
There are 60 cones, 30 red. Team consists of up.
And let's play now.
Team consists of up to 2 driver operators, a human player, a coach, and a robot. Each match is played with 4 randomly selected teams, 2 per alliance. But each alliance is only allowed 1 human player. Your opponent for one match may be your partner for another. Robots must be built from materials specified in the game manual and fit within an 18-inch sizing tool, but may expand after the match begins. The game element is a 4-inch diameter by 5-inch tall plastic cone. There are 60 cones, 30 red and 30 blue. Teams may also use their custom-designed beacons in gameplay. The game is played on a 12-foot square playing field with a foam tile floor and 1-foot-high walls. Various sized junctions are placed across the field, including 9 ground junctions. In addition, there are 8 low, 4 medium, and 4 high junctions. These junctions are mounted on flexible springs and might not be perfectly vertical. Taped-off substations are centered on both sides. In each corner are taped-off terminals. In the front and back of the field are taped stripes to help robots find cone stacks. There are 4 signals placed on the field. 4 unique navigation images are positioned on the field wall. And outside of the field are the red and blue Alliance stations. Before each match, cones are stacked in the substation storage areas and inside the playing fields. Custom beacons are also placed in the substation storage areas. Teams place their robots on the field, touching the wall between the substations and terminals. Each team may preload 1 cone into their robot. The 3-sided signal is then randomized. Each image references a specific parking target during match play. If a team designs their own signal sleeve, it can be used to gain additional points. The field and players are now ready. The match begins with a 30-second autonomous period. During this period, there are a number of ways for teams to score, using only pre-programmed instructions and sensor inputs. Each cone secured on a junction earns points. 2 points for the ground junction, 3 points for the low junction, 4 points for the medium junction, and 5 points for the high junction. A robot parked in their Alliance substation or terminal earns 2 points. If a robot's sensors correctly read the randomized signal, it can park in the corresponding signal zone to earn 10 points. However, parking in the proper signal zone shown by a custom signal sleeve will earn 20 points. Following the autonomous period is the 2-minute driver-controlled period. During this period, human players may introduce new cones into the substations. Each cone that is placed in its matching color terminal earns 1 point. Securing cones in junctions earns the same points as during the autonomous period. 2 points for the ground junction, 3 points for the low, 4 points for medium, and 5 points for the high junction. The last 30 seconds of the driver-controlled period is the end game. Robots may continue scoring cones, but there are also ways to earn bonus points. Alliances earn points for owning a junction. This can be accomplished in 2 ways. An alliance owns the junction if their colored cone is scored on top. This earns an additional 3 points. The junction can also be owned by capping it with a beacon. This earns 10 additional points and prevents the opposing alliance from recapturing that junction. An alliance earns 20 points by completing a circuit. This is done by owning a continuous path of junctions from one terminal to the other. And if a robot is parked in either of their alliance terminals, it earns 2 points. All cones scored during the autonomous period count again if they remain in place at the end of the match. There are many ways to score in power play, but there are also rules that, if not followed, will deduct points from your alliance. For example, robots may not de-score opposing alliance cones or beacons. A robot may not block or interfere with an opposing alliance attempting to score. A robot must be completely outside of a substation in order to score a cone or a beacon. Robots may control or possess only 1 cone and 1 beacon at a time. Scoring elements may not be launched, and robots may not deliberately remove game elements from the playing field. This has been a brief summary of this season's game, Power Play, presented by Raytheon Technologies. For complete rules, please read both game manuals and check the Q&A forum. And always remember the most important rule in First Tech Challenge: gracious professionalism. Good luck, teams, and have a great season.
All right, so with that in mind, as a brief summary for this season, we're going to go over Robot in 2 days.
Okay, well, I guess Robot in today's kind of just made a big old cube. We put a vertical inside, and for our guide mechanism, it was kind of just tweezers that would like go to the top of one kind of like split apart to hold it with friction. And once it would get over the phone, it would just drop down. It was all right, but it wasn't perfect. So I guess some things that we learned about Robot in 2 days. I'm gonna read off. All right. Right, so we thought the tweezers were pretty effective from a top-down point of view, since we didn't have to like go up against the wall or deal with the normal side gripper. I guess the size was a problem, since it was kind of bulky and the space between the cones, or the space between the poles when there is like cones on both of them is kind of small. So it was a little difficult to maneuver, but mechanisms were alright for this field. So it was just a big old grid, and we kind of do it. We did it. Autumn was easy to do, and I guess driving was not hard to get used to. But that's about it.
Now, to highlight one of those points, we really stuck to the idea of like a taller robot being able to circumvent all the poles on the field, which gave us the idea for Tallbot, which we're going to go ahead and play for you now.
So the chassis you're seeing here is kind of just like a test base that we wanted to see like whether the idea of a tall robot would work. And you can see that it's like super unstable. The two halves of the robot are trying to like drive apart. And so this kind of like test taught us that maybe that isn't the best idea. And we went on to try the robot that we have now.
And so even though mechanisms were like the optimal choice for this field, we decided to go with a differential drive chassis instead, mostly because a differential drive chassis is the most common one used in the real world, right? You don't see mechanisms going out into like construction sites or really anywhere except for smooth surfaces. And this is one of the few implementations of smooth surfaces, but to give ourselves more of a challenge, we decided to incorporate differential drive. And then, so a blast from the past. This current version of the robot is a robot that never saw competition 2 years ago when COVID hit. There were a few modifications we made to it, like this gripper, the LED panels, this nudge stick, and we're going to go into detail about a few of those now.
So here's just a little demonstration of our robot at competition before we go into more detail about how it was built.
You can see some of the advantages that we really wanted to use here, like the long arm and the custom gripper.
And one of the main things we noticed was we want to be able to circumvent the field without necessarily moving the chassis of the robot itself. And by using the turret and the turntable and our long arm, and we wanted to see how many advantages we would get from this instead of doing what all the other robots were doing and moving across the entire field itself. And now we'll be going in depth about our gripper design. So our gripper is a small bulb gripper, which is positioned inside of a bell guide. And on top of that, we have a servo and a sensor mount. And in the image itself, you can see that it is locked in position, ready to move one of the cones onto one of the junctions.
Oh my God, I need some more.
The robot really should be on the ground, guys.
Yeah.
The camera's
Let's start
gonna
moving
be- camera. Huh? I've been working.
And so the bulb gripper inside, which we have a picture of on the next slide, basically it has a small hole at the top with which we use the screws. And when you pull the screw up vertically using the servo, the bulb gripper itself expands out and lodges itself into the cone. And it's a very reliable gripping system because it doesn't rely on claws or anything along those lines. It grips the cone from the inside, something we want to implement after seeing how useful the tweezers on our robot in 2 days design. However, the amount of space we had and the amount of precision that would be required using this design was insane because it was a 7.9 square centimeter area that we would have for tolerance. So we decided that we would implement a bell guide with a cleared bottom, so we could have much more. We would have a much easier time controlling it, and it would be more autonomously. And as you can see, there is a 8.6% increase in performance.
So now we move on to the arm and the spring, which has two rings of freedom. So we have the shoulder here that controls the angle, and we have the three linear slides that come up and out. And this maximum tension. This can basically include almost anywhere on the field. For the nudge stick. So we've had a lot of problems with micro adjusting to get placement of cones. So usually our drivers will spend like 5, 4, maybe even 10 seconds sometimes trying to just get the gripper over the hole. And the nudge stick allows us to just align it with the gripper. So no matter where the arm is moving, the hole moves with it. So the chassis consists of an electronic slip ring, a turntable, a motor for the turntable, and then the 2 motors for the wheels, which allows us to have a full 360-degree motion around the field, and it alleviates sort of the time necessary to pick up, grab a cone, place it down, and repeat. And then finally, just for decoration of sorts, we have our custom LED panels, which display our number and alliance marker accordingly. And so far, we haven't had any problems using it. Nope.
Can you do that again? Sorry. I hope you can see it and the exposure isn't too high.
That's okay. If anything, if you guys could talk a little louder towards the microphone, it might help.
All right, we'll do. How about this one? All right, so now we're going to move on to our autonomous behaviors.
So we have 5 main forms of autonomous in our robot. So right now we detect where we're supposed to park. There's a memory system that makes it easier to drive. We have inverse kinematics, which again makes most of the autonomous is is not actually for the autonomous period. It's mostly for like taking the load off the drivers and making the robot perform more efficiently. We have scoring patterns, which allow for maximum control. We also have a new thing called grid drive, which allows the robot to drive itself to different locations on the field. Next slide. So what we're using is OpenCV, which is basically a collection of like computer vision algorithms. It's open source. It's been used in FTC for like years, and it's written in native code for maximum efficiency. So right now, we're using OpenCV to detect which one of these markers the camera is seeing. And based off that, we choose a location on the field to park it. So one would be, if it's facing this one, this is going to be 1, 2, 3. It corresponds to different parking locations on the field. And these things are just like April tags. We use Team 6547's tutorial to implement it into our code. And there's different designs for each like ID, and we should detect which ID is currently shown. So our plans for OpenCV are we want to detect the poles with the camera built into the robot. And to do that, we have a process that basically allows the camera to see like this yellow and determines like where it is relative to the robot. So first it goes through normalization, which accounts for varying lighting conditions. It gets rid of noise. It creates a black and white image based on like what color it wants to see, and then it creates like a blob around the black and white to get the relative location of the pole. And we're using FTC dashboard, which is it's basically just a not a website, but it's a local web server that basically allows the robot or the computer to communicate with the robot and change like differing values. So I can show a little demo of that.
You're not actually, are you connected to the?
No, but I guess
we can come back to that.
Yeah, we can come back to that. Yeah, it's really been helpful for like tuning the individual like components on the robot and making sure the code is working correctly. So I'll show off the memory function that I talked about earlier. So
Oh, that's kind of what we come off the split.
yeah, I'm not the main driver. So basically, when you pick up the code over track, and then go to a default location, when you first pick it up, and then once you place it down, it basically marks the location where you picked up and dropped the cone. So the next thing was in the way. That's
It's an early demonstration of the IMU tipping.
yeah.
Do we have to load up?
No, I think it's on. So that's another problem we found is basically when the robot starts to tip, since we're using a gravity-based IMU, that I'll talk about later, the arm tries to correct itself by basically the arm press that when it tips, the arm press itself by moving upwards, which makes the robot tilt even more. So it's just a feedback loop, which causes the robot to just tip over. And we tried adding a code bit to fix that, but as you can see, it wasn't quite working the way we wanted it to.
By the way, these are a lot of the changes that happened last night.
Yeah.
So the arm being it's clearly detuned from where it needs to be and where it was earlier. So this is all about like they just changed their kinematics, and he's going to talk about that in a second. And the PID tuning hasn't like caught up with it yet.
No.
So we're expecting it'll be pretty bad today.
Work in progress.
Yeah.
So what it should do is it should memorize where you picked up and dropped the cone, and then automatically select it between them if it's working correctly, which
That is not right.
is not.
And that is
So
yeah.
there's probably something that I did to make it do that.
Did-
But I'll show off the inverse kinematics, which is working a lot better. So basically what we can do is we can go up. So instead of using instead of controlling the angle directly and the extension directly, you can go up, down, and out, and then back, keeping the same height or distance whichever one you want to keep. And that makes driving a lot easier and placing cones on the poles.
Well, make that more clear. At the last meet, the driver had to control the angle of the shoulder and the extension of the arm directly. And when you change one, the height changes. You know, the height will change regardless. And generally, they want it to keep at a consistent height for a particular target. So the inverse kinematics is the way to sort of solve that, but again, it hasn't been completely tuned.
Yeah, and we have a little demo for that. So this is something I did last night just to go off. So what it should do is it should move the cone or the cone gripper in a circle relative to a location in space, and it does that relatively well. But as you can see, it's a little jittery and give you some tuning. But
So-
also,
You probably can't see it super well, but
yeah.
can you get a camera on it?
Get it to me.
Camera is pointed at it.
So how do you measure? You're talking height of the end effector, right? So how do you measure that?
It's all relative to basically the axle where it's mounted, and we have different offsets. Just like we have a height offset, we have.
I don't think that's the question. So, Carl, you're asking how we verify that it's actually maintaining its height
Yeah.
right now, right? So it's just visual feedback at this point because we don't have a distance sensor on there, but we could put a distance sensor on there pointing down to see if it's maintaining its height. We wouldn't probably do that during the match because there's robots and other debris around on the field and things like that, so you can get false readings. But for calibration purposes, it would be good for them to put a distance sensor pointing down, and they can verify that it's sort of maintaining its height. It's clearly not, and he's going to talk about how they need to add some feet forward, something on the PID to maintain the height a little bit better.
Yeah.
So I guess by inverse kinematics in this slide, do you mean that instead of measuring angle and distance, that it's just doing some math? So you are measuring the angle internally. It's measuring the angle and extension, but you're closing the loop around the point you want it to be in space.
Yes, that's what we're doing. So you can specify a target height and a target distance relative to the robot, and it'll just go to there. It does some calculations, and
But it's sorted out. Okay.
And if you were to drive the robot around, that place would still still maintained.
Yeah.
On the field,
So,
so it'll still orbit the same location.
Huh.
Even though the robot's driving around, so it should, or not.
Well, that's still impressive. Okay.
It did last night, but
Yeah, we tried
yeah.
Huh.
Maybe something's wrong with the odometry? Oh. I think it
No.
just crashed.
Nope.
Yep, it just crashed.
Demo fail.
Yep.
We call that the demo effect.
Yeah.
Oh, it's. Okay, it fully crashed. So it's gonna take a bit.
Power cycle required for that one.
Yep.
Go on your next one.
Yeah. So, scrolling patterns. Basically, so the point of the game is to control as many like different poles as possible. And we noticed that during competitions, we'd only stay in like 2 or 3 squares, and then just score, like continuously score from that square. So if you're in this square, for example, you'd go for the highest ones first, get the maximum points, and then you'd go for the lowest ones, and it would keep like each time the robot would go to different poles to basically just vary where it places the cones, and that gives you like many more points. You get for each pole you get a certain number of points, not even for scoring, for controlling that pole. And so you want to place cones on as many poles as possible and get more points. If that makes sense. You get control points. You control a pole, you get more points. And so basically the driver is going to specify a pole to go to, starting like the pole to go to, and then the robot will go through a certain routine of like placing cones. So for example, one routine would, like if it was right here, we go to this pole first, then this pole, then probably this pole, and this pole, and this circle to get as many like control as many poles as possible.
So to make it clear, the driver is not making these decisions. It's a preloaded scoring routine. And the robot's responsible for getting it as close to the top of the pole as possible. And then the driver just makes the decision if it's good enough or that they need to do micro adjustments to score.
Yeah. I'll talk about grid drive now, and so to get, which is
not actually implemented yet.
It's not implemented yet, but the concept's there. So basically, what we have now is we're using sensor fusion of these 2 motors, the ones that control the wheels, and basically using that, we can know the XY location of the robot relative to its starting position, and so we can get the location of the robot on the field at all times. And that makes it so that does 2 things actually. So one, so these poles are in fixed locations each time the field is set. So we can actually go to a pole automatically without needing drivers to do anything. And then the drivers can fine tune the location and then drop the cone. And even if the robot is like in a different location on the field, we'll still go to this one point because it knows its location and knows the location of here. And doing some more inverse kinematics, it can navigate to this pole and then drop the cone. So, and then
You're talking about grid drive, so
yeah,
you do have to move every once in a while.
Yeah. And then the other thing that the sensor fusion does in localization is grid drive. So as you can see, it's basically just a grid, and you can drive in between the poles. And using the location of the robot, you can actually like automatically navigate the robot and have the robot drive itself to different locations on the field without running into anything. So let's say this is 0-0. You can have it move here, and then have it do a left turn, and then move like a couple squares over to go place a cone on one of these poles or pick up a cone. So that makes the transition from Auton to teleop much easier, because during Auton, there's like 3 locations where you end up. Then you can automatically drive to the location where we want the robot to basically stay for the entire game, and that makes the robot more efficient, because the robot usually the drivers are not quite that accurate to not run into stuff, and so they'll hit like a couple of these poles on the way to going to the location. And with grid drive, it automatically drives in between the poles and doesn't hit them, and so it makes the robot much faster to drive places. Yes, that's basically drive. And so we went through 3 methods of getting the angle of this crane. So one of them was the built-in encoder on the motor. This one here. And we found that this encoder has a lot of slop. So even if it moves like this much, the motor won't actually read a change in value. And so that just was not working for us. And so then we added a dedicated encoder right here. And that just measures the change in the angle of the shaft. And so that was a lot more accurate, and it was precise enough to be used like for a long period of time. But every time we started the robot, we need to calibrate this, and so we'd have to go up, and then back down to get the full range, and then that would be our calibration. And we need to do that every single time, and that made like tuning the robot very difficult and very time consuming. And so our final and current design is to use IMU, and it's gravity corrected. So basically, it'll always read the angle relative to the ground, even if you don't do any calibration on it. And so that allows like much more rapid testing, and it's pretty much as accurate as this encoder. And so we basically just use this for everything, and I don't think we even use this one at all, or this one. And yeah, so there's a cool thing I'll show you. It may take some time. And you can see the video, right? It holds its position even though the robot is actually tipping. Yeah. But one problem we found with using this IMU is when the robot starts tipping, it creates a feedback loop and causes the robot to tip even more because it's moving this giant crane around. And I can show that pretty easily. What?
You can show it if they have questions about it. What about it?
Yeah. That's pretty much it for the autonomous behaviors and things that.
My turn? So, on the build side of things, you'll notice, as we talked about earlier, this is an older chassis that we've kind of like turned into a robot that we can use for this challenge. So on this slide, progression, you're kind of just seeing on the left, you have the model of the older robot that we used, was that 2 or 3 years ago? And how it's kind of changed. You can see there are only a few changes between the 2 chassis, like the gripper, and This rod is a little bit different, but most of it's largely the same. And so naturally, since this robot wasn't built for this challenge, there are a lot of changes that needed to be made to it. Next slide. So in this sketch, you can kind of see some of the changes that we want to make to the base. We have, first of all, one of the big problems that we have with this robot is that it can't really navigate the junctions very easily because it's just so wide. So on the new robot, we wanted to make it a smaller diameter and also cut off these edges here so that when the robot is driving through the junction, it's not hitting them. Because when there's cones on the junctions, the space in between them is just so small. We don't want to put that. We don't want to put that very little tolerance on the drivers or the coders. It just makes it way easier. So that's one of the changes we wanted to make. The other change we wanted to make was a second arm, since we want this robot to be able to grab elements from across the field and then deposit them wherever. So this bigger sketch that you can see with the two arms, that'll kind of show you what I mean by that. You can see, hopefully if it's pulled up, you can see on the right, we have this carbon fiber two-axis arm. And basically what that part's going to do is it's going to shoot out in the front. And that way this robot will be able to sit in one location on the field. And the arm, this arm will be depositing and the other arm will be grabbing and we'll do a transfer. So you'll have the one arm grabbing a cone, pulling back, transferring to this arm, and then this arm will do its thing, deposit onto junctions. And we do have a provisional model for that on the next slide. So here you can kind of see the bare bones of it. We're still working out the details of all of these models, all of the changes to the second version. But you can see that carriage with the wheels and how it might shoot out with two linear slides. Next slide. The other thing that we wanted to change about this chassis is the wheels. So we like having custom wheels. It's just a good judging thing to do. Also, it gives us more control over the compressibility of them. And so we're switching to a custom wheel design, and thank you, Gabriel. We've kind of already printed tires for it. So on the side, you can see the construction. It's different 3D printed parts and custom CNC parts. And 3D printed TPU tire, and that'll replace this almost exactly. It's the same dimensions. But making it custom design allows us to kind of switch down the space a little bit more to help us fit in the second arm and also control all of the variables of the wheel rather than just using something stock. Oh, and yeah, the last thing we wanted to change is that this arm is really, really heavy. The stages that we're using on it are just super thick. They're steel. So we wanted to change that. We switched to a smaller linear slide design, and we've added a fourth stage so that it can reach across the field. And this robot will be very long because of it, and a lot lighter, hopefully. That's it. Those are all the changes we're making, I think. Yeah, that's all the slides. We're ready to go into questions.
You're gonna demo Auton? It's broken. It's fully broken.
Well, I'll test it since I fixed it.
Yeah.
It should be fixed. But no.
Battery has?
12.3 volts.
Yeah.
12.4 volts.
Too low.
Oh, too low. You are on time.
Awesome job, guys.
Yeah, that's pretty cool. That's a lot of progress so far.
I have a question about the IK control for the arm. How is the path from one pre-programmed position to the next computed? Is it like a random?
So answer your question. So
that's the scoring pattern you're asking
the scoring
about?
pattern.
So what?
The scoring pattern for the robot. Is that right?
No, I'm not. I'm asking about we've got the mode, the autonomous assist mode, where it reaches over to the stack of cones picks up a cone, then reaches to the where it last picked up a cone, reaches to the pole that it last dropped a cone on. And you talked about using IK for that. And my understanding of IK is, the beginning and ending poses, and you have to compute a series of intermediate poses or a series of motor motions that transition the gripper from one to the other.
Yeah. Okay.
And there's a typically a random algorithm. Forget the name of it. That's used, but I'm wondering how you guys are computing the path that the arm should follow from one pose to the next.
So our method's not very intelligent. So basically the robot only has, it's gonna have 3 like poses really that just switches between, and it just goes to them directly. There's no like randomness or anything. So if the pickup pose, which will be on the cone stack, so they'll pick up a cone. So they'll get an intermediate pose where it just makes it so it won't hit any of the poles while turning. It'll turn it to whatever pole it will score on, and then it goes to wherever that pole is. If that makes sense.
Oh, I see. So it's a fixed 2 endpoints plus 1 middle point, and you just run the motors as fast as it'll go to, and whatever path it takes as a result of the motor speeds is whatever it takes. Is that correct?
Yeah, that's pretty much it.
There's no avoidance of like poles that are nearby, so it'll just slam right into them if the path is non-optimal for your location.
Yeah.
So it's a simplified inverse kinematics where there's always a solution. When you have a bunch of different degrees of freedom on a complex arm, then you got situations where you've got nonlinear equations to solve, and there might be multiple solutions, and it gets really complicated. But this is not required because there's only 2 degrees of freedom at work here, 3 if you include the turret, and there's no like attempt to avoid obstacles that might be in the way.
It is a 3 DOF arm, and because you need to count the turret because it's a part of the motion, a part of the path, and it is a well-known and unsolved problem. Kudos for taking on a difficult problem, because finding the shortest path, the best path between 2 arbitrary points is, boy, I've seen some arms and some vehicles do some strange things in choosing random paths.
Intermediate points,
So I have an observation on that actually, and it struck me from the very first time I tipped over, and that is, and it's going to be, I think, even maybe more.
Hold on, Carl. I gotta say that's just a hilarious statement. The very first time it tipped over.
Okay. Well, that we saw that we okay. Anyhow,
it's well deserved. Well earned.
That's how you learn. That's all right. It's all good.
No, I love it.
I wouldn't be the first person to have experienced that myself. I know y'all. Okay, so anyhow, and I don't even know a robot. I can fall over on my own. What I was going to say is that it strikes me that as you're going to make the diameter of the platform smaller, you will be even more subject to that kind of tipping risk. So, and then in terms of but I think it relates, I think there's maybe an approach, if you haven't already thought of it, that ties in with the last thing on how do you pick, with the 3 DOF, how do you pick shortest path between 2 points? And it strikes me that if you want to minimize the tipping, what you would do is draw the mass in towards the center of the platform before you turn.
Yeah, that's
so grab the cone, pull it in, spin, stick it out.
That is what they're doing.
Yeah, that's what we're doing right now.
Okay.
And also,
the tipping is only when it's really super extended, right? Also, I believe that they aren't actually changing their wheelbase.
no, the wheelbase is not changing. It's just the diameter of the chassis, and that's only changing like half an inch. But that half of inch will make a giant difference.
Okay, so it's more footprint than a mass distribution.
Yeah, and the other thing is that arm is going to get a lot lighter, and there's going to be another part of the robot that shoots off in the other direction. So we're hoping that the second design will be a lot less vulnerable to tipping.
Yeah.
So if I could share something I saw at the competition on Saturday that might be applicable here. It was two arms that extended from the robot. They actually had a different intended purpose, which was to scoop and push cones along. But you could imagine, you know how cranes have legs that extend and then they drop down feet? You can imagine some stabilization feet that drop down during the turret movement.
Especially if you get to where both of the new arms are reaching to the same side.
They should always be in opposite directions.
Should always be opposite. Okay.
The one that's dedicated to picking up cones is going to be pointing mostly to the perimeters of the field, and the other one is going to be scoring on the poles to the interior of the field.
Yeah, that might be a suggestion, is to consider stabilization feet that extend during arm motion. And then back to the IK problem, a suggestion there might be, since the operator does the first movement between the cone stack and whatever the target, wherever the target terminal is, maybe you could, rather than having just one intermediate stored point, record a stored point during the operator's control movement, say every second or a couple of seconds, and that would control the path that it uses during autonomous arm manipulation better.
That's an interesting point that I had not thought of.
I didn't actually follow that. Can you sort of re-describe that, Paul?
Yeah, so the current algorithm has essentially 3 points: starting point, an intermediate point, and an end point when using the autonomous motion. And that the arm will take whatever path it takes based on motor speeds as they may happen to be. But the path is, the endpoints are actually defined by the operator. It's a kind of a record mode in a sense. Right. And so the idea was to, when it's recording the motion under operator control, to take a snapshot of the intermediate poses between, say, every second or two as the operator moves the arm, and then when it's under autonomous mode, cycle through those pose instructions. So maybe there's 20 or 30 poses that it just runs through real fast in a continuous kind of manner to control the path that the arm takes when it's in running autonomously.
I see what you're saying. Yeah, I get it.
Yeah, that would definitely help with avoiding pulls, especially during dropping.
But I think that they're trying to get away from the whole memory function, right? That's a short-term fix before they had the scoring targets fully or the scoring patterns implemented. So the scoring patterns, think of it as an optimized, predefined set of targets that they want to hit from one particular location, right? So one particular source of cones, one particular location of the robot on the field, and it's only the arm that's doing the motions. And by explicitly defining which path they want it to go on, then it's sort of like takes that out, because they can optimize that so that they do it in the right sequence where it's not going to hit anything. It's not super like smart algorithmically, but it's a way to sort of predetermine how the robot's going to coordinate multiple scores from one location. But they haven't proven that out yet, so that's still under development. I think the code's mostly there, but again, this is one of those things that's really, really hard to test when the arm is detuned like it is right now. And they just converted to the IK driving of the arm, so they got to get that fixed real fast.
Have they thought about using possibly like a counterweight on the arm to help stabilize it?
Yeah, we thought of that. The problem is, if you have a counterweight here, it won't fit inside the sizing cube because we have an 18 by 18 by 18 like limit, and right now we're barely fitting in. And so if you have a counterweight, it won't fit inside the sizing cube. And then another problem with that is it'll increase the inertia on the turret. And so when you want to turn the turret, it'll end up turning the base of the robot as well, which is not what we want to do.
And it also makes it hard to fine tune the location of the turret, the angle, because once you get it moving, it wants to keep on moving.
Yeah.
So the angular momentum is a big problem. And I think they already spoke about the underarm, right? That's going to serve as a counterweight function, at least at the chassis level, right? Because when it's extended, it'll both prevent compression in that direction, and you'd have to lift it in order to lift it off the robot. So I
missed the underarms. Are those the legs like big cranes have?
They're not really. It's a deployable intake arm. There was only one slide on it, and I think it was, or there were two slides. So,
the second arm.
Yeah. So there's a second arm, and then the next slide after that. Is it actually showing the full screen?
I think you should take that in.
Can you go to the next slide? So that shows like the base of the underarm deploying from the chassis on a linear slide. So that extra mass is further out, and that'll like act as that sort of acts as a counterweight in one direction. So it's like it's not multi-directional like a crane stabilizer, a set of stabilizer legs.
Yeah. A question about how the operator controls the arm when they're reaching up or reaching to grab a cone or to drop a cone. Are they controlling? I thought I heard that they control the extension of the arm and the angle of the arm. Is that correct?
That's what they used to do.
That was the previous.
As of like day before yesterday.
Well,
well,
a week ago. It's been implemented.
And not for competition. It hasn't.
No, not for competition.
And it's sort of detuned still. So
yeah,
they can demo that a little bit more. Are you going to be able to run Auton, or is that a no go?
You can try it.
Yeah. Okay. So where they specify a target height and target distance. We had that. We had a feature like that in one of the robots I worked on at Endeavor, and they called it Fly the Gripper, which I think is a kind of a catchy name for it.
Called it what?
Fly the Gripper. And,
Fly the Gripper. Yeah. That is cool. Yeah. That is what they were trying to show with their orbit test, but I think we've got some work to do to demo that a little bit better and make it, get better camera angles on it. But yeah, that's exactly right. It's about thinking of that end effector as something that you just freely manipulate in space, and you don't really worry about how the robot, it actually has to control its extension and angle, because that's what what it really has. But you don't want to think about that because it makes it much more complicated to control. Yeah.
Yeah, that's great.
I love that term, fly the gripper.
Yeah,
I think we're going to use that one. Yeah.
Yeah, these are teleoperated robots, and they had a joystick, and and so you'd fly the gripper with the joystick.
Yep. That is what you're doing now.
Well,
Yeah.
we're using triggers.
Huh?
We're not using the joystick for both. We're using triggers for extension.
Yeah, it's the same.
Oh, well, yeah, but yeah, you could use joysticks, but you'd have to go to the second controller, second gamepad for that.
It'd be like driving. It'd be joystick, right? Like driving the chassis, but you're driving the
Yeah.
gripper.
Exactly. Yeah.
Same driving thing, I guess.
How do you control the height?
Height is
That would probably be the trigger. Yeah, you decide. I mean, the one thing is you're controlling X and Y, right?
Rotation, right?
So that's probably one joystick, and then you control height separately because you got less height. You don't need to worry about height as much because once you have a predefined pole as your target, hopefully the robot's just going to maintain the right approach height for it, right? That's the plan, isn't it?
Seems like it would be the joystick would be rotation and height, not X and Y and height.
Yeah, it's rotation and height right now. So
No, but you'd want it to be X and Y. Right?
Well, ultimately, but for the operator, wouldn't you want it to? If you're just looking at it, the operator's sitting off to the arena area. I mean, off to the side, the alliance area, and looking in. Don't you want to have the operator's visual feedback on that, not the XY coordinates?
Well, if you think about it, the operator is always in the same location relative to the field, and it's doing all of its like target selection in absolute field mode, right? So it understands its orientation and its position on the field, and so you could choose to not have the driver put themselves visually at the source, at the base of the arm, but just from the outside, just tell it to go, left and right on the field, to the correct location.
Well, I've been away from this for a while, but since that's the case, since all the targets and all the poles and everything is in fixed positions, why does the operator even need to look at the field? In other words, why isn't it completely autonomous?
Well, that's the goal.
yeah,
That's going to be hard to get there. I think that they should be talking about this. But
Yeah.
that is the goal.
So-
Lance, you want to talk a bit?
Yeah, I'll talk a bit about that. So we can. The kinematic model we're using right now is not it's not perfect. It's close enough to where the drivers can do fine small movements to get it placed on the pole. But that's another thing. We're trying to tune it to be exact, or have another system account for the imprecise nature of the crane in the model. So that's what the nudge stick is actually for. More a little bit.
it's
We'll drive it and show them.
Awesome.
We're gonna try. You're gonna try Auton?
right?
Okay, try Auton. They're gonna try Auton. Is it pointing at the robot camera?
We're
Yeah.
on.
Robots in view.
Yeah. It's probably gonna fail miserably,
Yeah.
particularly when it tries to score the preloaded drone. That's probably where it's gonna go bad.
Yeah.
So right there, it's reading the April time.
Yeah, we know it's supposed to go to position 2.
Wow, that is,
see how
it's gonna go bad. It's gonna go bad. Yeah,
you see how badly tuned it is.
yeah, that was a feedback loop right there. Is that because of the angle? That's an angle you didn't test for in your anti-tipping code, which was written in about 30 minutes or 20 minutes last night. Yeah. 5? Really? 5 minutes? Okay.
I'm an idiot.
Yeah. So there's no wonder it didn't quite. It's not still about yet.
Something I noticed is that the gripper has 1 degree of freedom and it oscillates quite a lot. I was wondering if you could put some either damping or active control on the angle to keep it pointed downwards. Because it seemed like it was struggling, or the operator was struggling maybe to get it stable over the top of the terminal.
Well, that oscillation right now is worse than I've ever seen it. And it's clearly a PID tuning thing. It's like that wasn't the operator doing that. That was
He's talking about
He's talking about this.
thing.
no, I know, but it was
Yeah,
because
yeah.
it was going back and forth that it was causing it to swing so much.
And in the future, we're gonna motorize it anyway because
Okay, cool.
for the
Cool.
transfer, this has to split in half, which means that this has to be able to be controlled by the
Cool.
code.
Cool.
Yeah.
And you could put an accelerometer on it, and then you could control it to always point downwards.
We actually don't need an accelerometer because we have one here, and this angle is always the same. So we can actually use this angle to determine what position this should be in.
Well, not when it's freely rotating. Like when it's oscillating, you're not going to know what angle that's in.
Well, we're talking about motorizing it. Motorizing.
Yeah, once it's motorized, once you basically what servo. Once you get a servo on there, it's gonna you're gonna be able to control it.
Yeah.
But then you're asking the servo to like handle a lot of load, right?
Yeah.
It really wants to swing at the mass.
And that's more weight.
So normally it doesn't oscillate that much, and it settles pretty quickly. And there is sort of a friction. So yeah, see that right there? That's not driver. That's not the driver doing that. That's bad.
Yeah.
Right. The arm is oscillating, and then that's feeding into shaking of the gripper.
Right.
Yeah.
It's
Hey,
underneath
why-
your arm flex or something.
Is it too much trouble to, I don't know, do an impulse response on it and run any desired control movement through a Bode filter so that it's inverse transfer function to wipe out the oscillation before it gets there?
So I don't think that's necessary. I think they just need to retune the PID.
And I know it would have to change that the filter would have to be changing continuously as the arm gets longer because the resonant frequency keeps changing. But
Yeah, that's right. Yeah.
that would just wipe it out, I think. That's a lot of fun to watch though.
It is a lot of fun to watch. It's going crazy.
That's like the Pixar Luxor lamp just gave up.
Yeah.
It's amazing it hasn't destroyed itself, actually.
Yeah.
Well, the bell is almost totally shattered at this point. Time to put on a new one.
But really, is it too much? Is it impractical to build in the response of the system into the intermediate software that goes between the control request and the output?
So there's different. So yeah, there's like different kinds of filters that we could put in there. They're just doing a PID filter, basically PID control, and that again, what you're seeing is a remarkably bad detuning from the changes that were made last night. So it doesn't normally look this bad. In fact, there was like a recording earlier in the presentation where it showed what it normally is like, and they just need to get it back to that. It's because under IK it's behaving differently, but they need to add a feed forward term to their PID, pretty likely. And that is, you're right about that. That changes dynamically with the amount of extension that the arm is under at any point in time. Because there's different basically gravity load depending on their height and their extension.
Okay, thank you. So that's partly already in there. Okay, good. Thank you.
Yeah, it's just badly tuned right now. Yeah. But if you want to make further recommendations about this, I didn't hear what specific filter you were talking about. Were you talking about a particle filter or a Kalman or something?
I've never done one of these myself, but I've seen one of the teams out in one of the big the 200-pound machines, and they could accelerate it and stop it instantaneously, and the thing was like 4 feet tall, and it didn't vibrate at all. And it's
Yeah.
not because it was massive. I mean, they were making it as light as they could because they wanted to have a lot of stuff on it. But they would take hammers and hit the thing and record do the vibration analysis of the entire chassis. And then anytime they did an input to the motors, it was modified by that, knowing what the chassis was going to do based on that. And it could just accelerate and stop, scary. It's like, it would almost look like stop motion, claymation kind of stuff. So anyway, but I don't know how to do that. I mean, I know how they made the measurements with just hitting the thing and doing impulse response measurements with microphones and accelerometers. But as far as how they coded that into the software, I don't know.
Oh, okay.
Thinking about this from the presentation point of view and presenting to the judges, I think there's a really innovative feature, which is that arm that swings down and steadies, touches the pole and steadies it and stops it from swinging to stabilize it so the cone can be dropped. And it was mentioned, whoever was narrating that was talking to that slide did talk about, well, that's what the arm does. But I think if you just wrap that in an expression like, we think one of the creative things that we did on our arm assembly is this thing that stops it from vibrating, that would, in my mind, line you up for the I forget the name of the award for creativity.
The Innovate.
Innovate, yeah, the Innovate Award, because that really is creative.
Yeah, it doesn't get to work. I mean, it does technically work right now, but this is where, for it to work properly, it needs to have, you can see it right there, I guess, but they need to get their height control much better, right? Because otherwise it'll miss the top of the pole and it won't work.
Yeah, but the existence of that wand that swings against the pole to stabilize it and stop it from flopping around in the air, I think is really clever and deserves maybe more highlighting for its creativity in the presentation, is really what I'm saying.
Okay, thanks.
So continuing on with the presentation, did I remember you got 5 minutes and you want to try and boil this down somehow?
Yeah. We're going to have to choose to not mention a lot of things, right?
And talk a lot faster.
Yeah.
More
well, I
precisely.
mean, this is they hadn't practiced this presentation yet. So.
That's all right. I honestly, I would explicitly not. I would recommend not talking faster.
Me too.
Because there was parts, especially I forget where, but there was parts when the speech was so fast it was very difficult to follow.
Yeah.
So to me, the challenge, which will gain you more points, probably is to figure out economy of words. So how can you get the stronger story across in fewer words so that you don't have to speak faster?
Yep, I agree. Yep.
And it's hard. I have a tendency also. I want to explain every detail.
Yeah.
I want to race through because I know a fixed time. So obviously the answer is to cram more detail in a fixed time.
Yeah, me too.
What that does though is that devalues the value of any one word or any one thought. So whatever you say, it gets lost in the noise in a way.
So people only intake so many concepts in a certain amount of time. If you push past that, you're basically they lose all of it almost.
Pretty much.
Yeah.
So I would suggest that in terms of deciding what you want to say, I would do kind of a top-down approach in the way that, could you in a few words describe what kinds of information do you think the judges would like to see to give you the most points for your presentation? So I would start with that.
Yeah, I'd address it from the you know what the categories for awards are, and you know the definitions of them. So try and hit as many of those categories as you can in a compelling way.
Yeah, when they get to their portfolio, that they always organize it according to awards, and try to embed some hints into the presentation as to which award we're suggesting that particular slide is relevant to.
Yeah, because as a judge, you don't get to see, other than if you're in the categories that specifically inspect the report, you don't get to see the report by and large because you don't have time. You're moving through these teams like lickety split, and and so for most, like 5 out of the 7 awards, really don't get any significant look from the or input from the report. It's all in the presentation.
Yeah. Well, they will. What they did last year was they used the report as their presentation. So in other words, it kind of like forced the panel that they were seeing in the morning to absorb the portfolio. And I don't know necessarily how well that worked, but that was the choice that they made last year.
I mean, I'll tell you, we struggled because we were we were late getting started and the teams were backed up. And then you just get, you have the 5-minute uninterrupted presentation, then you have 10 minutes Q&A, then you send them on your way and you got 5 minutes deliberation. That 5 minutes is not enough for a 3 or 4 person judge team to take a look through a report. So fine if the presentation is based around the report, but it's really the impressions from the presentation that the judges for Innovate and those other categories that aren't solely on the report work from.
Yeah. And you have to present for all of the awards, not just the technical stuff, right? What they were showing today was just the technical stuff. So they got to make time.
Absolutely. Yeah.
Okay, so points aside, I'd like to make a comment or two on just like storyboard, like how you organize the concepts in the presentation. And well, the first thought would be if you have your 5-minute time box, then imagine that, I don't know, even rapid fire, 2 or 3 slides a minute is pretty fast, unless they're just images, right?
Yeah.
So you probably only have time for maybe 5 or 10 slides, really, with any meat on them, aside from the team name. 5 or 10 slides. And I haven't outlined everything, but there's like basically two things that I thought would help me as an audience getting my arms around this robot. And the first would be overall strategy. What am I trying to do with it? And the second would be the build-in implementation. And maybe the third might be the handover between it has a lot of semi-autonomous functions and autonomous functions kind of blended together. And to me, that's kind of interesting, especially playing with my wife's Tesla in auto drive mode. It's a very clever thing to do effectively, and it's hard to do to make it a nice, smooth, let's leverage the robot, but let's take control when we need to and not have it be this jerky mess in between.
Yeah.
So those are the areas that I thought were interesting. And then, so does that make sense? Strategy, implementation, then like Auton manual hand sharing. But then under strategy, the things that, and even the first strategy. So here are the 3 points that caught my eye as I look back. So the first is that you've taken the overall strategy to leverage autonomous as much as possible to get things close. And then you use the human for the last step. And then that seems to apply to driving around the field. It seems to apply to remembering the pick and place positions for the cone, because if I heard right, you got this absolute thing where it knows the location of every pole, the tip of every pole in the field.
Yep.
That's pretty cool to me because it's got that pre-mapped. And then the whole maximized scoring plan. It sounds like it's got like an algorithm in there where it does the thinking for you to figure out, well, if I go here, then there, then there, then there, that's I can get the most points. Subject to someone else capturing a pole. So I would love to hear more about that overall strategy early on in the presentation, because that kind of sets the stage for what I'm going to see later on. And then also, like, what caught my eye was as much as possible. Okay, so one strategy I had a bullet is that you're going to use autonomous to get close, human for the last step. And then as much as possible, the second part of the strategy, as much as possible, you want to maximize speed and points. You're going to like drive to one part on the field and then plop the base and then just use the turret and these two arms. So to me, that's a pretty pivotal choice early on. And then later on, if somebody asks, well, why didn't you use mechanisms? You can get into that. But early on, I mean, that's your pivotal strategy. That's core of your strategy, right?
Yeah, you're right.
So I would think about like the first few slides or somewhere early on saying, well, we're approaching this challenge this way, and then outline those key things you're proud of that are like set the course for your design. And then the build and implementation. Okay, so what I picked up from this presentation today was you started off with a prototype based on an older platform, the COVID platform, whatever, and now you're tweaking it to optimize it for this power play, maybe a little smaller footprint, lots of carbon fiber. Why? Strength and weight, or strength to weight ratio, and inverse kinematics, and then that arm that Paul brought up. So those were the interesting things to me on the implementation, and also the choice between differential versus mechanism. But to me, that's separate. That's after the strategy part. I want to see, as the audience, personally, I mean, I like to see what's the overall game plan up front.
Sounds good to me.
We were asking some of the teams, what was their strategy and how did the techniques or the implementation of the robot support that strategy? And we got some good answers. And that's a way to think about it.
Yeah, the essential strategy with this robot versus the tall robot that could be driving over the poles was to minimize the total amount of field navigation. And I think that bears out because you see a lot of traffic between the four robots on the field. And you got robots waiting on other robots to get to necessary locations, or having to extend their driving further around the grid. And so, but it's yet to be borne out that, until they have the scoring patterns working and tuned, it's hard to say, yeah, they figured out that strategy.
Yeah.
So in other words, they made a huge strategic bet on that ability for that arm to reach across multiple tiles, and we haven't proven it out yet. Hopefully, they'll have that by the third meet and be able to demonstrate it for the tournament.
I wanted to just springboarding off of that. I wanted to raise an observation, and I don't know whether it's good or bad, but it's certainly interesting, that in the video of the rules of the game that you showed at the beginning, it said one of the rules is you're not allowed to interfere with another robot. And so what this design, one of the things, whether intentionally or not, that this design does is it kind of hogs the field during the period that the arm is extended. It prevents anyone else from crossing that part of the field. And so it slows down the opposition, but also possibly the alliance partner. So it's maybe a thought, something to think about how you can optimize the slowing down of the opposition while you're consuming space with your long arm, and simultaneously not inhibiting your alliance partner.
Yeah, there's actually so when their robot is doing its memory function and kind of score, and it's sort of facing into the field, or the arm is, I think it might. I haven't seen it get in the way right so far of other robots, partly because the arm is like up high. For the most part, we're just doing most of our scoring on the tall poles. And that's actually, like, we don't want to get into what's called defensive play, where you're trying to block other teams, because that's not allowed. But if you are trying to score, then you are allowed to follow any path that allows you to, that is part of your scoring approach. So then you can't be like charged with a penalty for blocking another robot. The only thing that we have, the thing that we haven't run into yet, is like an aggressive robot on the other side coming up near our robot, and it's possible then that our, the lack of collision avoidance could become a problem. And if we were to hit another robot with our arm, that would be interesting on how the referees would interpret that.
Yeah, and so I wonder if you ought to have a pause button to stop arm motion if it looks like it's going to hit another robot.
Yeah, I think that's a great idea. There's some things that is that last little bit of going fully autonomous is very, very challenging, because then you have to have collision avoidance. You have to have super precise placement on the field, and so we're not betting on that right now. But it would be cool to add that. So there, we could add some collision.
Even in manual mode, when it's doing that autonomous arm movement from the source to the destination, you'd maybe want a pause button in case the arm was going to transition through the space occupied by another robot.
Yep, that's a great idea. It's going to be interesting to. It's actually not going to be that tough to implement either, because at any point in time we know where the robot is, and it's just variables that are governing where the target is. So you can just like snap up its current position, run the backwards through the IK, and then set that as your target, and that should freeze the arm.
Yeah, I got a question from earlier. What if everything in the arena has a known position and the robot localizes itself by looking at the pictures on the side and stuff like that? What was the camera doing for the blob detection of the poles? Was it looking for the angle of them, or was it trying to determine where the poles were, or why did it need to know that?
That's not fully implemented yet, but the idea is this is back to the it does the same thing as the nudge stick, right? In that it allows precise targeting of the poles. So the angle to the pole, the theta angle looking down on the field, is probably the hardest part to get right. And so nudge stick is one way to go, and a camera identifying exactly where it is, when it's underneath the grabber or the gripper. That's the other approach. So I don't know that they're necessarily. It's probably a matter of trying to implement both, but because if they get the vision correct, then they can sort of, before they start extending the arm, they can have their targeting finer. Remember, these poles are on springs, and they're actually not perfectly vertical, right? But they got to get to the very top of them. And once they get beat up during a match, they'll drift a little bit. So So the vision can help sort of localize that a little bit better.
But
Okay.
I'm glad you asked that, John, because I wondered that too. The vision gives you an azimuth heading, but it doesn't give you range.
Now, there's also a distance sensor on the nudge stick.
Oh,
It's a 2 meter time of flight sensor.
oh, oh.
But also the diameter or the width of the poles is a known or fixed thing, so you would know that regardless of how it's angled.
Yeah, that's a constant, the width of the poles. Yeah, I think the what they're running into is just the level of precision required for all of this.
Yeah.
Right. Being able to say, you know, it's within, you know, a few inches versus 1 inch versus, you know, how close do you have to get? So.
And I know I'm dragging you back to the presentation instead of the good stuff that Carl was talking about, which is I agree with absolutely. And Paul, why is it, or is it that the poles can be distorted enough that you can't just have a? Well, I answered my own question. I was going to say, couldn't your cone grab the pole and realign it before it dropped the target on it? But I answered that my own question because the cone doesn't have a big enough base. Never mind. All right.
Yeah. Well, I mean, we do it. The cone. Yeah, the cone basically defines how accurate we need to be. The base of that cone defines how accurate we need to be positioning over the pole. Because it's the only part, you know, and that's you know, the nudge stick can help align it in the according to the overhead angle, and then the distance sensor can get it close enough. When it stops oscillating, the distance sensor should be able to get it close enough so that even that, it's possible that the driver won't have to make that decision of when to release the cone.
So I saw Kareem's head on a couple of the shots. Is he going to mind getting whacked by the terminal posts? That was great.
I started with the blast from the past.
Yeah,
that was awesome. Blast from the past guy.
Huh?
Just like super glue it on the top about.
Oh, you don't want to put my head on the real robot. No.
Would that be one of the special custom pieces that claims a flag as your own, a pole as your own?
Yeah. All right.
Yeah, when we come up with the number of custom parts, we'll include like 30 of those just to include the numbers.
Don't you need to put it on the parts list?
Yeah, no, we don't need to show that.
Just scan them. Okay, so what do you do? How does this automatic goal planning thing work? How does that handle the case that you know, there are 3 other robots in there and one of them is friendly and 2 are not? What happens if you've got the plan to go capture a pole, but somebody snags it before you do?
You can stack.
Yeah, you can stack on. Yeah, you can have multiple cones stacked on top of each other. Yeah.
I thought like in the video they showed a crown on top, and once you did that, you couldn't.
That's only one.
And that's only an end game. That's with 30 seconds.
So that's the last 30 seconds of the entire game. So there's still 2 minutes where scoring patterns, you can do it like wherever you want.
Okay.
And it's a driver determined. So if there's a beacon on one of these poles, then the driver can hit a button, it will skip this pole and go to the next pole in the sequence.
Okay, so you got that covered. Nice.
Yeah.
There's only a maximum of 4 poles that can be owned that way. If every robot puts its own beacon out, and then the rest are always up for grabs, and they can be, you know, they can change ownership based on who gets there last.
Okay.
It's just an incremental points for the ownership, right? You still get all the points for the cones that you put on that terminal, on that pole.
Yeah, that's right. the ownership only amounts to 3 points per pole, but it does seem to add up because there's a lot of junctions here, right? And so it does seem to flip who wins the match fairly often.
Oh.
These are
Interesting.
Otherwise, you would focus on like what they were doing in their previous matches is focusing on just stacking everything on one tall pole because that's the maximum point per cone.
Yeah.
Right. And that like gives you 5 per cone versus 4 on the next lower one. And that's where their memory function was coming in pretty well because they would just keep going back to the same pole. But then you're giving up the 3 ownership points per pole. It's 3 for ownership, and it's 10 if it's a beacon on top.
Yeah, so it would actually be better to actually go for a smaller pole that doesn't have a cone on it than it would to place on a pole that already has a cone.
Yep. And then those end game points also factor in to like the ranking, the tiebreaker points. But it's the second set of tiebreaker points, so it doesn't actually matter that much. I haven't seen it actually make a difference yet because the first tiebreaker points are based on your Auton scores. So it's really important to get your Auton scores as high as possible. And they need to get their precision up so that they can get to scoring multiple cones during all time.
Very fun.
Cool stuff.
Well, thanks, guys. Really appreciate your attention and input.
You got it.
I think they heard a lot of things that they'll be paying attention to and adapting for.
Cool.
In the coming weeks.
Well, thank you for coming in and showing us this. It's like tremendously cool and a lot of fun.
I think it'll be a lot more impressive once it's tuned properly. Because it looked better just a few weeks ago, and we need to get it back. Huh?
It's impressive, even as it is. It's impressive. So
yeah.
Definitely. If the competition is smart, they'll watch this channel.
Okay, and that's so. So, are you guys comfortable, or still okay to post this on YouTube video clips or DPRG clips?
Yeah, you have the option of letting it post or keeping it private. Your call.
Post it.
Huh?
Post it.
Yeah, we're happy to show our tremendous fails. Yeah.
We can do some views.
Way to go! Way to go!
I will take that.
Let's just dare the competition to try and do what you're doing. That's awesome. That's the way to do it. Put it out there.
Well, there's going to be some teams who are pulling this kind of stuff. I haven't seen another team doing something like this. Almost all of them are doing vertical lifts and driving to the poles. So I'm sure there are some other teams that are doing like an arm that's reaching over things. But I haven't seen any that are reaching as far as this one. But again, we're also dumping ourselves over onto the field, and
that's just today. You get a couple more minutes of coding, it'll stop.
They haven't done that. They haven't done that in an actual competition, the tipping over thing.
Yeah,
so this is new behavior, and so yeah, they got to just figure it out.
I'll get there.
All right.
Well, cool.
Thank you.
Thank you.
Thanks a bunch.
Hopefully they'll have a chance to present an improved situation next month.
See, I think that'd be cool just to see the progression in
Well,
one
yeah,
quality time.
This was a strategy. This was an attempt to set the bar low so that we could show more progress, right?
Yeah.